Okay, welcome to another advanced mechanics video with circular motion, and in here we're going to be looking at calculating the normal force of what you would experience when you were at these three positions in a loop-the-loop. Alright, so let's have a look here. Right, we know that we have Fg going down and we have the normal force going up, and we said from previous that Fn is equal to Fg, and so therefore the normal force you experience would be mg, and so your mass is 15, well, we're going to change that to 150 grams. Right, so that's a little toy car, for example. So we have 150 grams, which means we have to convert that to kilograms. So putting in 150 grams, which is 0.15 kilos, we get 1.47 kilograms per meters per second squared, and of course that is newtons. So that is the normal force that you would experience sitting up there. Then of course we start to go down the ride. As it's going down here, it's going to come down and start to accelerate, start to change direction, which therefore it's undergoing acceleration, centripetal acceleration. So it's going down here. So this is like a dip here. Okay, I've drawn the circle a little bit wonky, but I guess we could extend it out here. You're going through a change in direction, so you're accelerating. Your velocity is 4.43 meters per second squared. So my question is, well, what is the normal force that you experience, and therefore your apparent weight? How is it? What's it down there? Well, we derived this equation before, but let's just go through it again just to reinforce the concepts. We have Fg going down, and we have the normal force going up, and we have centripetal force going up. And we said that the forces going into the circle are positive. So F net, or the centripetal force, is mv squared over r. We have F normal minus Fg. And so F normal is equal to mv squared on r plus mg. We've got the mass of 0.15. Velocity 4.43 squared. We're running out of room there. Divided by r. Now we haven't got any r data here, so let's just make the r here. Let's make that 20 centimeters. That means it's 0.2 meters. And then of course we have to plus mg, and mg is 1.47, so let's just plus 1.47. So when we do that calculation, you should end up with 16.2 newtons. We started off with 1.47 newtons at the bottom of a dip. Right, at the bottom of a dip, the normal force you experience is a lot heavier, so of course therefore you feel that push up on your seat and you experience that as your apparent weight. What about when we get to the top here? Well, the velocity is pretty fast at 4.43, but then it starts losing energy, starts losing kinetic energy. It goes up because it's gaining gravitational potential energy as it goes up. I'm going to look at that in a future video. So as it's going up here, it's losing kinetic energy, gaining gravitational potential energy. So when it gets to the top here, it has its speed is less. So let's see, or its velocity is less. So let's see what the normal force is up there. So remember the normal force, we've got centripetal force going into the center. We've got the normal force going into the center. And we've also got gravity, Fg. And so, let's see if we can write that here. We've got Fc, the net force acting on it, is equal to the normal force plus mg, which is the gravitational force. So therefore, our normal force is going to be Fc, which is our mv squared on r, take away mg. So let's see if we can plug in some values here. We've got 0.15. The velocity is 4.43, square that, divided by 0.2. But then we have to take away 1.47. And what do we get? So we have less normal force up the top here, but greater than what we had before, right? In terms of just sitting there, okay? Here's a question which we brought up before, is what would happen if the normal force was 0? So at the moment it's 7.35, but what would happen when it was 0? Well, you'd experience weightlessness at 0. You wouldn't feel the normal force of the seat pushing on you, and so therefore you experience a momentary weightlessness situation. Sometimes that happens in a ride, and that's why they've got the straps that hold you in and so you don't fall out, but momentum keeps you going around, but you feel a momentary that you're not touching the seat, and it scares the living you-know-what out of you, right? So that's how the normal force changes as you move around through this scenario. Hopefully that makes sense, and we'll see in the next video where we start exploring how energy changes happen during our loop-the-loop and relating it to centripetal force. And I'll see you in the next video.